Okay, welcome everyone. In this video, we're going to talk about a new gas law today. And this gas law is called Charles' Law. And so I wanted to make sure that you've got your guided notes out and you're following along and filling them in as we go through these slides. But let's get started. So Charles was a French physicist. He lived in 1746 until 1823. And so what did he do? He found that the volume of a gas at constant pressure increased in a linear manner with temperature of the gas. So, in other words, let's look at these graphs down here and put it into words that we can understand. As the temperature of the gas, if we see here on the x-axis down here, as the temperature of the gas increases, we see that the volume, which is plotted on the y-axis, also increases. So there's a linear relationship between the temperature of a gas and its volume. And I wanted to kind of show you this graph here on the right, so this one over here. If you look at it, it's got different gases here, so 4 different gases, but each one you'll see, as temperature increases, so does the volume. And they've extrapolated, at the bottom you see these dashed lines here. Okay, this is called an extrapolation. And each one of these would connect at this point right here at about negative 273 degrees Celsius. Negative 273 degrees Celsius is a famous temperature. It's called absolute zero. It's the coldest temperature that you could possibly ever reach. And so what's interesting about it is they all extrapolate right here to have a volume of 0. So if you ever could get a gas to be as absolute 0, I guess it's theoretical, but it would have a volume of 0, which is take up no space, which is kind of interesting. Anyway, let's continue on. So the equation for Charles' law is this. V is equal to kT. Well, K is a constant, and V is volume. So volume is equal to the constant times the temperature. Another way, if we just rearrange this equation of writing it, would be like this. So volume over temperature is equal to a constant. Okay, I don't know what this constant is. Let's give it a number. So say volume over temperature is equal to 10. So if we look at this equation and kind of look at it mathematically here, if you increase the temperature of a gas, what would you have to do to volume in order for it to stay at this number 10, at a constant number? You would have to increase it. And so temperature and volume are have a relationship it's called a direct relationship. So if one goes up, the other one has to go up. Another way, let's look at the reverse way. Say volume over temperature equals 10. What if we decrease the temperature here? In order for this number to still be 10, we would have to decrease volume as well. And so the temperature and volume of the gas are directly related. As one goes up, the other one has to go up. If one goes down, the other one has to go down. Okay, and this puts it into words here. Volume is directly related to temperature. As the temperature of a gas goes up, so does its volume. Okay, so they have a direct relationship. Here's the equation that we're going to use the most in this chapter for Charles' law. So I'd like you to fill that out in your notes, and we're going to go over it. Okay, it says that V1 divided by T1 is equal to V2 divided by T2. Now, of course, let's go over the variables. V is for volume, T is for temperature, and the little 1 that we see right here and here, the 1 just tells us that's those variables' initials, so what we're starting with. The 2 over here tells us that's the volume and temperature final, or at the end, what it ends up being. And so when we plug in our variables, we have to be very careful in deciding what is the initial volume and temperature and what's the final volume and temperature of the gas. So, okay, that's Charles' law. V1 over T1 is equal to V2 over T2. Okay, that's basically it. We're going to summarize it now and then do a practice problem. Okay, the summary of Charles' law. Number 1, there is a direct relationship. So it's a direct relationship between volume and temperature of a gas. Number 2, as the temperature of a gas goes up, the volume of the gas also goes up, and vice versa. So if the temperature goes down, so does volume. Okay, there's a direct relationship there. This is the useful equation. We'll use it a lot from Charles' law. We have to be able to read a problem, plug in the variables, and come up with an answer. But there's one important key with Charles' law that we've got to talk about. Number 4 down here, very important. It says temperature must be reported in Kelvin. Kelvin is a unit of temperature that we don't see very often. We're familiar with Fahrenheit. We're somewhat familiar with Celsius. But you've probably never seen temperature measured in Kelvin. But it's just another unit of measurement for temperature. So there is conversion factors in order to go from Celsius to Kelvin. And so that's what you will have to do, because when you plug in temperature right here and right here, it's got to be in Kelvin. Okay, so let's figure out how to go from Celsius to Kelvin. That's going to be a skill you're going to have to learn. To convert from Celsius to Kelvin, use the following equation. I would like you to write this equation down in your books. So Kelvin, that's what the K, this capital K is, Kelvin, is equal to the degrees Celsius plus 273. So if they give us degrees Celsius, we just simply add 273 to it, and you've got your answer in Kelvin. If we look at this equation in a little more detail, what if we had a negative 273 degrees Celsius? So Kelvin is equal to a negative 273 degrees Celsius plus 273. Well, that would be equal to 0 Kelvin. And 0 Kelvin is a very famous temperature. It's known as absolute zero. It's the coldest temperature that you could possibly ever reach. Absolute zero has never been reached in a lab. We get very, very close, but nobody has really ever got to absolute zero, the coldest temperature possible. So it's kind of a theoretical idea here, but the particles, if you heat a substance up, its particles move faster. If you decrease the temperature of a substance, particles will move much slower. So if you get to a cold temperature, the particles move slower. And it's kind of a theory, but at absolute zero is when all that molecular motion, all the particles would stop moving. And it would be very interesting to see the properties that different substances have if the molecules stop moving. But nobody's ever got to absolute zero yet. So, okay. We're going to do some practice problems where we convert all of the following Celsius temperatures into Kelvin. So, number 1, how would you convert 25 degrees Celsius to Kelvin? Okay, let's do that. We're going to use this equation right here. So our degrees Celsius is 25, so 25 plus 273. And so you'll see that's 298 Kelvin. Now this is going to be an important number for us in this chapter. If you recognize 25 degrees Celsius, this is room temperature. 25 degrees Celsius is room temperature. And a lot of the experiments that are being done with gases are done at room temperature. So you will always see, maybe not always, but a lot of times you're going to see experiments done at 25 degrees Celsius. Well, that's 298 Kelvin. Okay, let's do number 2. Let's convert this one to Kelvin. Okay. So we've got a minus 150 plus 273. So a minus 150 plus 273 is equal to 123 Kelvin. 123 Kelvin. It's a very cold temperature. Remember, room temperature is 298 Kelvin. And so if you're down to 123 Kelvin, that's a very cold temperature. Very, very cold. All right, I've got one more. 100 degrees Celsius is boiling, so it's going to be, it's a pretty warm temperature. So let's convert that to Kelvin. We take 100 plus 273, and we get 373 Kelvin. All right, so there's a few examples of how to go from Celsius to Kelvin. And remember, in Charles' law, we have to go to Kelvin for the temperature. I've got one practice problem here for Charles' law. So let's go over it. It's practice problem number 5. And it says a sample of gas at 15 degrees Celsius and 1 atmosphere of pressure has the volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere of pressure? Okay, when I approach a problem like this, there's a lot of information given, isn't there? What I always like to do is underline what they give us. Okay, they gave us 15 degrees Celsius, 1 atmosphere of pressure, and the volume was 2.58 liters. And then it's going to change things on us. We're going to increase the temperature, and it gives us 1 atmosphere again. So why did they give us atmospheres if they didn't change it? So pressure is not changing here. Are we going to use it? If it's not changing, no. So it's not changing. We don't need to put it into our equation. So the only thing that is changing is temperature. Temperature is increasing. And it wants us to know what the volume will be. What the volume of this gas is going to be. So we're dealing with two variables that are changing. We're dealing with temperature that's changing and also volume. And that's exactly what Charles' law is for. We're going to write the equation for Charles' law, which says that V1 over T1 is equal to V2 over T2. Okay? Now that we know we're going to use Charles' law, one of the best things that you can do first is switch your degrees Celsius here to Kelvin. So let's do 15 plus 273. And that will tell you what it is in Kelvin. 288 Kelvin. Let's change this one to Kelvin. So 38 plus 273. 38 plus 273. And I'm getting 311 Kelvin. Okay, so we're going to use Kelvin when we plug them in. Okay, before we start the problem, it might be a good idea to kind of think about what's happening here. We are increasing the temperature of this gas. So it's going from 15 to 38 degrees Celsius. So we're increasing temperature. The temperature is increasing. And according to Charles' law, they're directly related. So what should volume do? Well, it should also go up. Let's make sure that happens. Let's see if we can get that. So what I'm going to do now is plug in my variables. Volume initially was 2.58 liters. So 2.58 liters divided by T1. Temperature 1 was 15 degrees Celsius, but remember, you've got to change it to Kelvin. That's 288 Kelvin. Okay, that is equal to V2. Well, it didn't tell us what the final volume is. That's what it's asking us to solve for here, is what the final volume will be. Okay, and T2, the final temperature, was 38 degrees Celsius, but remember, we've got to go to Kelvin. So that's 311 Kelvin. Okay, so at this point, we have an equation with one unknown. We don't know V2. So what we've got to do now is isolate this variable, V2. How would you guys do that? We want to get rid of this 311 Kelvin. We're dividing it. So what I would do is times both sides by 311 Kelvin. Remember, whatever you do to one side, you've got to do to the other side in an equation. Okay, and why did we do that? Well, what's 311 Kelvin divided by 311 Kelvin? Anything divided by itself is 1. So it cancels out on the right side. So let me rewrite what we have so far. So V2 is equal to 311 Kelvin times 2.58 liters divided by 288 Kelvin. And now we can see that our Kelvin divided by Kelvin will cancel out. And so V2 is equal to 311 times 2.58 divided by 288. So let me put that in my calculator. 311 times 2.58. And then divide that answer by 288. And so V2, the final volume of this gas, will be 2.79. And if Kelvin's canceled out, the only units that we're left with are liters. So the volume of that gas will be 2.79 liters. Now that we're done, let's see if it did in fact increase in volume. So the initial volume was 2.58, and our final volume went up to 2.79. So it did increase. Temperature goes up, so should your volume. Okay, that's it for Charles' Law. I hope that this helps understand how the temperature and the volume of a gas are related, and they're directly related. Before I stop, I just wanted to review some of the more important things from this video. Okay? So as temperature goes up, so does the volume of a gas. If temperature goes down, then the volume of a gas will go down. We're going to use this equation for Charles' Law. V1 over T1 is equal to V2 over T2. When you plug a temperature in, remember it's got to be in Kelvin. Okay, and how do we find kelvins? Well, Kelvin is equal to your degrees Celsius plus 273. So there's your conversion factor, or how you convert from Celsius to Kelvin. Okay, now that we're done with the notes, you guys now know enough to complete a worksheet in your student workbook. So I'd like you to complete, it's called Charles' Law Worksheet in the student workbook. And I hope this helped.